go there. There's a link in the teaching section to OPLSS stuff, and then there's a link from there to the course materials. Okay, so while you're getting that, let's talk about the lab from yesterday. And the thing that I want to talk about is this notion of dependent pattern matching. We kind of introduced it yesterday and used it some, but didn't get very formal about what's going on. So the idea with dependent pattern matching is that in general, when you're trying to prove something like map length, okay, we have an argument h of type length x is n. Okay? And the question is, what does it mean to case analyze something of type length x is n? And the idea in general is that when you have something of type length x is n, what you do is, for each data type constructor C, which has type pi x colon a, so like every data type constructor has some number of arguments, and then includes length x's prime n prime. Right? So each data type constructor for length has the form, given some arguments, I'm going to include length x's prime and n prime, where these are expressions. So I don't mean x's prime is a variable and n prime is a variable. That can be any Agda expression. Right? And then these expressions can, of course, involve these variables. So what you do is, for each data type constructor C, you do unification. So you unify x's equals x's prime, n equals n prime. So this is unification just like in ML or Haskell type inference. You compare the two and try to find a substitution that makes them equal. And when you do this, unification is either going to succeed or fail. And if it fails, then there's no case for the constructor C. And if it succeeds, then you apply the substitution that unification gives you to the clause. Okay? So this is an abstract description of what's going on with dependent pattern matching. And now we're going to do a couple examples to illustrate what it means in specific for this example. But this idea of unifying the types of the constructors against the thing you have is really important. Okay, so how does that work? Let's look at first the version where we case analyze. So here in map length, we can first case analyze L. So if we, or sorry, x's. So if we case analyze x's, then we get that case. And then if we go into the cons case, we can case analyze n. And then if we go in the successor of n case, let's look at what happens for this description in this case. So in this case, what we do is we have our h down there has type length x cons x's and successor of n. Okay? And now let's work through that description of an algorithm for the cons constructor lcons. So lcons has type, if I rename the variables, for all, what, n prime, I'll call them n prime, x's prime. And then what it comes up with is length of x prime cons x's prime, successor of n prime. Okay. So now what we do is we unify x cons x's equals x prime cons x's prime, and we unify successor of n equals successor of n prime. Okay, so we ask, find a substitution that makes these two terms, these two equations hold. Okay, so what equations do we get out of that unification? Oh, yeah, sorry. Arrow, then the hypothesis, arrow that. But that part of it's not relevant to this unification because the hypothesis that that x's has length n doesn't occur in the target type. Okay? So what equations do we get out of this unification? Solve that problem. Someone? Okay. We can say that x prime equals x. Yeah. X's prime equals x's, and n prime equals n. Okay? So just, if you want to make these two terms equal, then that matches that. So you say that that equals that, etc. Okay? So there's an interesting thing to note here, which is in this way of doing the proof, of where we split on L and then N, what we get is equations that define the constructor arguments in terms of other stuff. Okay? So what I mean by the constructor arguments is n prime, x's prime. Right? Here the equations can be thought of as defining the constructor's arguments to make the type come out right. Okay? So that's what I was calling inversion yesterday. I didn't quite have the story straight. The key property here, where you first look at the simply typed data and then analyze the dependently typed data, the thing to note is that you end up with a definition of the constructor's arguments in terms of stuff that's around. Okay?
Did you say the constructor? What exactly are you?
So I mean L colon colon. So L colon colon here is the C that we're talking about, right? So for each C, I'm doing the case for L colon colon. Okay? Does that make sense? All right. I want to look at one or two other ways of doing this proof and what happens with the unification. So another way of doing it is, instead, let's just case analyze the dependently typed data first. So then what happens is we have length of x is n, and L colon colon is going to have the same type as before. So when we do map length 2 and we just look at h, what we're going to do is we're going to unify x's equals x prime cons x's prime, and we're going to unify n equals successor of n prime. Okay? Let's see. Yeah, so if you case h, right? And when you solve this unification problem, well, it's a pretty easy unification problem to solve because it's variable equals stuff, right? But notice that if you interpret this as defining equations, here what we're doing is we're defining x's and n, okay? So when we have a type family, I just need a word here. I'm going to call these the indices of the type family, that is the arguments to the type constructor. Here what's happening is you're defining the indices of the type constructor in terms of the constructor's arguments. Okay? So here, x prime, x's prime, and n prime are held fixed, and you define x's and n in terms of them. And this is why dot patterns come up. So people were confused about dot patterns yesterday in lab. But the reason for the dot patterns that Agda inserted in the dot x cons x's and the dot successor of n is that when you do this unification, in this case, what Agda is figuring out is that those indices to length must have been x cons x's and successor of n for the nx and x's that are coming from the constructor. So the information's flowing the other way. Instead of defining the constructor's arguments in terms of the indices, we're defining the indices in terms of the constructor's arguments. Okay? So the dot pattern is saying this must have been something in order for it to type check. And the way that you uncover that information is by this kind of unification. Okay? So these two, oh yeah, question?
So just to confirm, it seems that you can move those dots around.
We're going to do that next. Yeah, okay. So just to, that's exactly the point I was going to make next. So these are two kind of extremal points on a spectrum. So in that version, you define all of the constructor's arguments in terms of the indices. In that version, you just define all of the indices in terms of the constructor's arguments. Okay? But you can actually do anything in between. So say that you case analyze L but not N here. Okay? So if you do, or X's, sorry. Okay. So now if in the cons case, so let's look at what we have. So here we have length of x cons x is n, but we haven't yet determined that the index n is a successor. So now if we case analyze h, okay, then in this case, we're kind of in between. What we're getting in this case is that, let me just write it over here. So in this case, we're getting that x cons x's equals x prime cons x's prime, but that n equals successor of n prime. So when you solve these unification constraints, you get that x equals x prime, x's equals x's prime. Okay, you get these three equations. So one of these, n equals successor of n prime, has to be interpreted as, can you change the n in the constructor arg to an n prime? So yeah, there, and in the argument to, yeah, that. Good. OK. So one of these has to be interpreted as n prime is coming from the constructor, OK, and n is defined in terms of it. But the x and x's are sort of ambiguous. You can either think of it as we're getting those from the list, and therefore the arguments to the constructor are forced. Or you can think of it as you can move the dot. So if you move the dot on x to the other one. Or you can think of it as we're getting it there, and that one is fixed. OK? But this idea that the main idea here, so this one is in between the two we had in the beginning, because some of the indices are forced to be something in terms of the constructor arguments. Some of the constructor arguments are forced to be something in terms of the indices. But the main point here is that we can have this sort of situation where you learn things about earlier arguments because of matching on later ones. And that's really the important point about dependent pattern matching. OK? Does that help clear up some of the confusion there? OK, good. Questions? All right. One more thing from the lab, if you just scroll down. If you look at the implicit args version, the only thing I wanted to point out is that when you do the implicit args version, map length here, some people were kind of uncomfortable about matching on these proof objects, like matching on the proof that length has some, that a list has some length or something like that. I just wanted to say, like, that's totally OK. That's what you should do. Right? So like, you don't need to case analyze the list or case analyze the number. Just match on the proof. OK, good? All right, if you have other questions from the lab, we can talk about them during the hands-on later today. And I want to get back to the red, black trees stuff and keep going with that. So if we go back to the stuff from yesterday, then where were we? So we'd written this code. We wrote balance and ins and black and root. So remember that black and root, right, is the function defined by empty goes to empty, node whatever color is sent to a black node. And yesterday we did a proof that the black and root, blah, 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 blah. OK, keep scrolling until we get to the implicit arg version. Yeah, OK. So yesterday we did a proof right there, black and root hyphen black height. Push that stuff that we're about to do today off of the screen. Yeah, OK. OK, good. So we did a proof that black and root black height has says if t has a black height n, then the black and root of t has black height something. OK? And one thing that's a little bit annoying about this proof is that in the code for black and root only has two cases. It has a case for empty and a case for a node of any color. But in the proof, we had to expand into three cases for empty, a red node, and a black node. OK? So that's a little bit annoying because we have to kind of copy and paste the same proof there. And when we get to other examples later in this development, it would get even more annoying because there would be even more stuff to copy and paste. So let's fix this problem. And the thing I want to point out here, the lesson, is that when you're doing this kind of programming, when you're doing certified programming, definitions matter a lot. So it's often the case that there's many equivalent ways to define a concept if you're sort of writing things on paper or something like that. You know, you can define it this way or that way. There's lots of equivalent definitions. But when you go to formalize something in a proof assistant like Agda, you really have to get the definition right. And there's not really any way to figure out what the right definition is a priori sometimes. So as you do this more, you get more experience. And being the right definition is very specific to individual proof assistants. Like what works well in Agda might not work well in Coq and vice versa, because different proof assistants have different features. But it's really important to be willing to play and experiment and try different definitions until you get the one that makes your proofs easy. So you really don't want to just sort of take a definition as given off the shelf and work with it. Really like play with your definitions. So with that in mind, let's revise has BH so that so if we go down, go down, go down, let's revise our definition of having a black height so that we can get a tighter proof for black and root black height. OK? So how do we want to do that? A little further up. You're too far down. OK, yeah. So there's the definition of has BH. OK. OK, so there's the definition we had yesterday. So what do you want to do to make it so that we only need one case for nodes in black and root black height? Yeah?
Well, the only difference between the two things, one is N and one is S.
Difference between HBH node red and HBH node black is the result height. OK? So let's make one constructor that somehow expresses both of those. So if we delete HBH node black and then rename HBH node red to just HBH node, OK, then let's see. Let's put a question mark for the red that's down on the bottom and the N that's down on the bottom, OK? Because those are the two things that are different, right? OK, so we can load that. Let's comment out black and root black height, because that's not going to work anymore. OK. Good. So now, how do we want to fill in the color of the node? Like that first goal there? Sorry?
I don't know what that is.
Okay, but just for the color, like there's nothing to case on here in the constructor, right? So here we're describing when a node has a black height, right? So what do we want to say? Yeah. Okay, good. Let's add an argument called c to the function and say, what we're now going to prove is that a node of any color c, so we can fill in that goal with c, and you'll have to load and then refine. Yeah, so a node of any color c has black height something, right, if stuff, okay? And now what we need to do is what? Sorry? Yeah, so we need to somehow relate the output color of the tree, relate the output height to the color, okay? We can do that by defining another inductive family. Let's call it color height, okay? So up above that, we'll define data color height. And color height is going to relate a color and two numbers. So it'll have type color, arrow nat, arrow set, where, okay? And now we're going to give this enough constructors to express the relation between colors, and then the two numbers are you're going to think of as the height of the subtrees and then the height of the result. Okay, so what's the first constructor? Let's call it ch-red for color height of a red of red. So that's going to have type given any n, which is a nat, color height something, something, something. Okay, and the first something is going to be red, because we're going to say how red acts. And then the next two arguments are going to be n, and then the result of a tree, red node, whose subtrees have height n. Okay, which is, if it's red, n. Yeah, because a red node doesn't increase the black height. So the height here is the black height, sorry, right? Okay. And then the color height for black is going to say, do that, color height, black, n, and now we get the successor event. So this is a relation that relates the triples red n, n, and black n successor event. Okay? So if we load that, we're good. And then what we need to do is to have HBH node take another natural number, let's call it m, and also in between L and R, we can put a proof that for the color C, N and M are related. And then the output there can just be M. Okay? Yeah?
Is there any reason color height was not made a function?
That I'll talk about right now. So you could also have defined color height as a function. There are some features of Agda that work better if you use inductive families than if you work with functions for exactly this reason. So if all of your inductive families are indexed by constructors, then this unification stuff works really well because constructors are injective and disjoint. But if you'd used a function here, then dependent pattern matching doesn't work as well. So yeah, this is a place where Agda and Coq are a little bit different. Like in Coq, you might be better off defining this as a function. But in Agda, we'll see how this works really nicely. OK, so now let's do black and root black height. Any questions on that transformation? OK, let's do black and root black height. So the empty case is the same. And for, let's see, so we'll need a case for a node. So in the next case, we have empty case is the same. Here we have black and root black height of HBH hyphen node. And now node takes three arguments, HL, and then let's call it CH for the color height, and HR. And if we need to put parens around node there, because otherwise it thinks it's a curried argument to the function. HR instead of HL. Yeah, great. OK, so now if we load and then look at what's in the goal there. OK, so now we see that we have L has some height, R has the same height, and then there's some color height stuff over here. But we can just ignore the color height stuff, okay? And on the right, we can just construct this, basically the same thing we wrote up above, which is over there, HBH hyphen node. Okay, and now we want to show that a black tree has a height. Okay, so what we need to do is we need to find a height for the left, a height for the right, and the appropriate relation for black. So the height for the left is going to be HL here. Okay, and then let's fill in HR in the second one. Okay, and now let's look at the type of the middle one. So here, what we need to do is we need to find some number, right? Because we're proving an existential, it's just got to be some number such that the color height of black of n1 is that number. Okay, and of course the number will be successor of n1, and we can just fill the goal with color height hyphen black. Okay.
Now, the dots in, I'm sorry, I can go back. I was just going to ask about the dots in that display.
Yeah. Okay, go back.
Information that you look at when you're looking at that
Okay.
context.
So the dots here, so like the dot L and dot R, when you have implicit arguments, those aren't in scope, right? So you don't have a name in your text that you're typing for L and R, but internally, of course, they're there, right? Because the implicit arguments are there. And dot is just Agda's way of notating. This is something that you can't refer to, right? Because it's an implicit argument. But here's what it's called in the cases here. Okay, that makes sense? Okay, so let's fill with CH black. Good. Okay, good. And then that one can just be underscore, because Agda's figured it out. So now what we've got is a proof that black has a height that's exactly the same as the code for black and root, right? The code for black and root says empty goes to empty, and node goes to node, where you take the color and you turn it black. The proof says empty, it goes to empty, node goes to node, where you ignore the color coming in and turn it black. Okay? Good. Ian, can you comment out the stuff from the length stuff so that we don't get all the length goals? So yeah, so like all of this demo stuff from up there. Good. Okay, great. Okay, questions about that?
What was the key there that you found in the
Control Q? No?
It's something that I defined.
Oh, like it's just an Emacs thing. There's Control Q for me, but there's like meta X. Okay. Yeah, it's just an Emacs command called comment region. Okay, good. So, questions so far? All right, let's go on with the proof. So, what should we do next? Let's do ins. Okay. So next what we'd like to prove is something about that recursive insertion function ins. And if we go back up to the definition of ins and take a look at it, then what does ins do to the black height of a tree? Well, empty, which has black height 1, gets set to a red node with 2 empty subtrees, so that also has black height 1. When we insert into a node, let's look at the equal case. In that case, we just keep the structure of the tree the same, so that has the same black height as the tree that we put in. Okay. And then in the other cases, we recursively insert, and then we call balance. And if you look at balance, balance rejiggers the tree, but it does it in such a way that it preserves the black height in the sense that it's the same black height as if we had just created a node. So what's going on in ins is, in fact, ins is preserving the black height of the tree as it does the insertion. And that invariant is really a constraint on how you color nodes when you balance, the fact that you want ins to do that. So let's do the proof that ins preserves the black height of the tree. So ins is now going, ins bh is going to be our proof that given any tree t, any natural number, or sorry, yeah, any pair of key and value that we're going to insert, if t coming in has black height n, then going out, ins t kv also has black height n. Okay? So now we can set this up, and we have ins bh of, let's call it h for has bh. Okay, good. Okay, and now if we look at what we have, we've got some stuff. And Agda doesn't choose the best names for k and v here. It calls them dot first and dot second. That's a little bit annoying, but whatever. They're implicit, so it's you kind of get what you type. So now what we want to do is do this proof. So what do you want to case on? Okay, how about h? So let's case on h. And when we case on h, okay, back up. So make case doesn't always work very well with implicit arguments. Sometimes it makes cases that don't in fact work. So like sometimes the thing it spits out doesn't actually then type check, and that's just like a bug in Agda. But what we can do here is make the kv argument explicit, and that'll clean this up some. So if we make kv, no, so just make it an explicit argument to the function. So if we make kv an explicit argument instead, just to get around this bug in make case, then this will go a little bit smoother. And then we want to bind kv before the h. Yeah, OK. So now this will go smoother, sorry. So like make case is just a tool, right? You can always write these cases out by hand by actually just like typing all of the characters if you get into trouble. But there's this bug in make case with implicit arguments where sometimes it doesn't quite work right. OK, but now we're in a good state. And what we want to show is that, so what happened here? We case analyzed HBA. We case analyzed the proof that it has a black height. That gave us two cases. In the process of case analyzing that, we learned what the tree T was, right? Because when the proof that T has a black height is HBH empty, T is empty by our rules for dependent pattern matching. We're propagating information from the constructor for the proof back to the indices. We're learning what T is, okay? Which is why, in this case, ins TKV reduces according to the rule for inserting into the empty tree, okay? So Agda is almost a little bit too magical in the sense that you kind of have to work through in your head, why is that the goal that I'm supposed to prove, right? You really should understand that rather than just like being like, OK, that's what I have to prove. Let's go, right? So you see how Agda got from one to the other? OK, so let's prove it. What we want to show is that this tree has black height 1. And the way I think we should do this is we should refine, at which point Agda will say, oh, it must be a node. And then we can refine, at which point Agda will say, oh, it must have been empty. And then we can refine, at which point Agda will say, that must be color height red. And we can refine, at which point it'll say HBH empty. Okay? So when these things are kind of forced by typing, just like mash on refine a little bit, and Agda will kind of write the proof for you. There's also some proof search built into Agda, which I don't want to tell you about too much yet because you'll abuse it. But that would have found this one in this case, too. OK, so on to the more interesting one, which is the node case. So if we look at the node case, what Agda prints out is kind of gross. And so let's actually explicitly name the implicit arguments to make it more readable. So if we name the implicit arguments, let's see, not there. Let's name the ones to node. So node should take what? So we can either scroll up and see what order they come in, or Ian can read it off the screen from the other one. Yeah, so node should take nm, yeah, nm C, L, R, and then let's call this K prime comma V prime. Okay. And then we can call that HL, CH, and HR. And then we can actually at the same time pattern match KV as K comma V, right? So we can break apart the key value there. Okay. And here we're just cleaning up stuff so that, giving more human readable names to the names that Agda chose. And now if we look at the goal, okay, it's at least a little bit better. Okay. So what this is saying is that you have to cover the case for inserting, actually, can you do a control U that? No, okay, right. Forgot that doesn't work on yours. Okay, so you have to cover the case for ins of this tree, KV, and then some stuff, okay? And you might be a little bit puzzled by what Agda is displaying there. So let me diagram that for you. So here what we have is ins of key compare value, node of stuff, and then KV, bar compare K prime. Okay? So that looks a little bit longer than you might expect, so let me explain the new pieces. So these key compare value are just the modules